a jacket, and then a coat, and then a snowsuit, and then mittens and gloves and boots and hats and super insulated houses. Why I'm not a fan. Hit the music. Hello and welcome to the Adding Energy Podcast, a podcast about energy usage, energy efficiency, and energy issues. I'm your host, Mr. McLean, but you can call me Sir. Today, I want to talk to you about super insulated homes. Now, this actually came about a while ago. I was having a conversation with a coworker about a building that was being built to passive house standards, and we had a specific savings goal. And he said, if you need more savings, you can just add more insulation. And I said, oh, that won't work. I then explained this phenomenon to him, and he said, you should tell more people. So this is me telling more people. So I'm familiar with a couple super insulated homes. One was in Massachusetts, had something like R80 walls, R100 insulated ceilings and roofs. There was one in Colorado that had like 75 for the walls and something like 110, 115 for the insulated ceilings and roofs. So I'm not just talking about, having R20 or 25 walls or R50 ceilings. The other thing that happened in 2018, a bunch of the code values jumped in the International Building Code. Now, that doesn't mean that it applies to where you live right now, but when they moved their values up, the high performance building standard also moved their numbers up. And so now we're starting to get some pretty big numbers for our values, especially in the colder climates. And I kind of wanted to approach this whole thing and get through some of the issues with super insulated homes. Now, by issues with super insulated homes, I don't mean that your walls are so thick that your doors become more hallways and your windows more like portholes. Not the fact that you can't use standard windows or doors without jambs and extensions, and that you have to put your siding on the thing that you hang on your insulation. That and the nightmare you create for the cable guy, all those things you can plan out with your owner, your designer, and your builder before you start construction. There's another thing that we don't normally talk about, and I'm going to start by blaming it on R value. In a lot of ways that we use R value, you would think you would solve for the perfect R value because we have a great equation for it. BTUs per hour, or Q, equals 1 over R value times surface area times temperature differential. And if you look at that equation, you quickly realize that the R value is the made-up engineer number. And it meets all the great criteria of a great meets all the criteria of a great made-up engineer number. If it's 1, it's small. If it's 100, it's big. And almost all your life, you're going to deal with numbers in between the 1 and the 100. So you take BTUs per hour equals area in square feet times temperature differential in degrees equals 1 over BTUs per hour per degree. Now you can go out into the real world and you can find square feet, you can find BTUs per hour, and you can find degrees Fahrenheit. You can't find anything else that has the same dimensions as K or R. So the problem that leads to is that if you wanted to build an R10 wall, you probably can't, given like stuff that's on the shelf at your local big box builder store. You can build like an 11 or a 13 or a 15. You can probably build an 8. You can probably build a 4. But to build a wall that would actually hold up a building, it's going to be tricky to make an R10. So you can't just solve for whatever value and say that's the value you're going to use. It's a number that we measure in a test stand. And then when you take that test stand out into the real world, you realize there's a lot of places we screw it up, right? Where walls come together in the middle of the wall, hitting a wall in the middle of the wall. When we put things like pipes and ducts and wires into walls, all those things we do kind of disturbs the test bed assembly of the standard exterior wall insulation value calculation. So to play this game, what I want to do is I want to use a building block, a unit cube. For those of you who've been doing homeschool teaching for the last year, I want to use the unit cube of the North American house, which in my eyes is the 1,000 square foot ranch. 1,000 square foot ranch is something like 25 by 40, 1 story, flat insulated ceiling, insulated walls. And for the purpose of this discussion, we're not going to care about windows or doors. We're not going to calculate for anything through a slab or a basement. We're also going to ignore ventilation and infiltration, which is the air that sneaks in and out, controlled or uncontrolled. We're going to specifically look at conduction through the ceiling and through the walls. The great thing about that 1,000 square foot ranch is that you end up with 1,000 square foot of insulated ceiling and basically 1,000 square foot of exterior wall given an 8-foot ceiling height. So for our value, let's make up a number. Oh, how about 1? Makes my math really easy. So Q, the amount of heat you have to put into that house, equals 1/1 times the area, roughly 2,000 square feet, times the temperature differential. Now for temperature differential, we're going to use a fairly robust heating climate. So I'm going to say it's 70 degrees inside and that it's 10 degrees outside. That gives us a 60 degree delta T. And so 2,000 times 60 times 1 equals 130,200 BTUs per hour. That's a number. It's also about the same amount of BTUs in a gallon of diesel or home heating fuel. So if you wanted to know how much an R1 wall would use on a design day, it would use about a gallon of oil an hour. Order of magnitude. That's a lot. Home heating fuel, $2.50 to $3 a gallon. Diesel, $3.50 to $4 a gallon. To do that for a whole day, that's a pretty big chunk of money. So let's change the R value. Let's get that knob for R value. Let's turn it up to 10. By turning it up to 10, you end up with now having a BTU per hour on the order of 13,000 BTUs per hour. Well, good news, now that gallon of fuel oil lasts 10 hours. So now for $10 or so, you heat your house for a day when it's 10 degrees outside. Okay, that makes sense. I've gone from 130,000 to 13,000. Let's turn the knob up to 20. So if you change your R value to 20, you're now at about 6,000 BTUs per hour. Wow, that's 6,000 BTUs per hour. That feels pretty good, right? You now get a day, basically, out of a gallon of home heating fuel. You can handle that. All right, R20, that's going to be our value. Now, some things are dependent upon the heat load that you're calculating. You're going to buy your heating system based off these numbers. And so going from R1 to R20, you've dropped a lot. And in fact, going from 10 to 20, you dropped about 7,000 BTUs per hour. That might be enough to drop you under one size of heating appliance. The heating appliances we're talking about, boilers, furnaces, usually come in like increments of 20,000 BTUs per hour, so like 60, 80, 100,000 BTUs per hour, or 25s, which would be 50, 75, 100, 125, 150,000 BTUs per hour. Increasing your R value from 10 to 20 might permit you to sneak under a size rather than having to jump up. So if you were at, let's say, 80,000 BTUs per hour, and you went from R10 to R20, you would then jump under the 75,000, and by jumping under the 75,000, that prevents you from having to buy the 100,000 BTU per hour boiler or furnace, and that would allow you to shrink your heating system, possibly the gas connection to it, possibly also the duct or the pipe or whatever else you're dealing with, and that can be very beneficial in first cost and life cost and everything. If you want to go crazy, we can go past R20. Well, let's go to R100. That's basically Spinal Tap's turning it up to 11. If you go all the way to R100 for your walls and your ceilings, you now end up with a load for the walls and ceilings of about 1,300 BTUs per hour. So that means that gallon of oil that used to last an hour now lasts 100 hours or 4 days. Well, 4 days of heating fuel, that's definitely going to help your heating bill. But there's more to it. Well, obviously you have your ventilation, you have your infiltration, you're going to add other things to that. But that number, 1,300 BTUs, that's like silly, right? 1,300 BTUs is like 500 watts. So a watt being about 3.5 BTUs. All right, yeah, you're about 500 watts. So you could heat your whole house with 500 watts. Or you could heat the walls and ceiling load with 500 watts. Maybe there's other issues with this. If you're an old gun like me, instead of using R value, we like to kind of quantify how these systems run with a concept known as balance point. And balance point works off this kind of a theory, that everything you do inside your house adds heat from you being in it, breathing, exercising, cooking, cleaning, and whatever, plus the energy you use for cooking, for lighting, for plugging TVs, laundry, water heater. All those things add heat to the space. We assume that over 24 hours, it's a relatively similar lump of heat every day, and that creates a point when the amount of heat you create balances out the amount of heating the home would require. And in fact, everything you do adds heat to the space except for exceptional, novel, crazy things like huge amounts of domestic water usage or cold water usage, and the other one being a heat pump water heater, which has a net cooling effect because it takes the heat out of the space, puts it in the water, and then goes down the drain warmer than it came in. So what does balance point look at? Well, let's finish up in this R value of 1. If you had a building that was R1, first of all, it's like 1/4-inch glass for walls and for ceilings. And you probably don't want to live in that house, and it probably doesn't stand on its own. But that R1 house, if you had 2 people in that 1,000 square foot house, you would put off something like an average of 2,000 BTUs per hour. Well, 2,000 BTUs per hour we can put back in as a Q, and then times 1 times 2,000 square feet gets us 1 degree temperature difference. So you can heat your R1 house with just the people in it and all the stuff they normally do down to 69 degrees. Well, let's throw our value away. Mostly because being that balance point's a really empirical thing, let's use actual houses that exist. So the first example of house I'm going to use, I'm going to call it Grandma's house. Now, I don't know where your grandma lives, but to me, Grandma's house was built something around the 1950s. It's either solid masonry, exterior walls, brick, block, concrete, plaster, all three, or it's 2x4s and studs with no insulation. These are very common, and if you've been in one of these houses, you kind of know that sometime in October, they get cold. So, what's the balance point of Grandma's house? Well, Grandma's house being that type of construction, you're going to have a balance point something like 60, maybe 65 degrees. Now, Grandma wouldn't turn the heat on when it was 60 degrees outside. They would wait for it to get to like 50 or 55, and when it gets to the point where it's cold inside the house, and they would put on slippers and they'd put on blankets and sweaters and those types of things. But if you were trying to maintain 70 degrees inside, just the baking, cleaning, and people would probably keep 1,000 square foot ranch at 70 degrees down to between 60 and 65. The next one I would call your childhood home. Now, your childhood home, I'm assuming, was built in the 80s, right? We have insulation. We have double pane windows. We have some of these things figured out. Those types of houses tended to have a balance point somewhere in the 50s. Could go as low as actually 50, depending on the number of people. But for 2 people in a 1,000 square foot house, 50 to 55 is probably not a crazy balance point. So that's a pretty good number, right? If you go to today's modern house, you're going all the way up to like R20 for walls, 40 to 60 for ceilings. We got, Energy Star windows. We've got house wrap. We got blower door testing. We're starting to get good at this stuff. The house doesn't need heating until, I'm going to say, you sneak under 50 degrees, right? 40s, maybe as low as 40. Most likely it's 45, 48, something like that. That's a pretty good amount of change that from the 50s to the 40s. Just by doing things like knowing how to insulate. Now we're at 2x6 construction or continuous insulation on the outside. We've done a bunch of things to do these things better, and we're getting a good handle on those things. If you go look at super insulated houses, mostly just due to the nature of everything else that's going on with them and how thick and massive their exterior walls end up being, they end up with really tight, really well insulated structures. And because of that, their balance points are crazy low. I've talked with people who say that their balance point of their house is usually someplace around freezing. The one in Colorado, they grew bananas in it, and they said they didn't have to turn the heating system on until water outside was freezing. That's a cold temperature to start needing heating. And so what you learn by looking at this is that the way you save energy with a super insulated house is not reducing the amount of BTUs it takes to heat those walls when it is cold outside, but the fact that you reduce the number of hours you are actually heating. So, we'll go back through this whole thing again. Grandma's house, needing heating at something like 60 degrees, that's about 6,000 hours annually of heating. When you get from that grandma's house to your childhood home, you go from 6,000 to about 5,000 hours. Now this is off like upstate New York type temperatures. You get to today's modern home, you've gone from 6,000 to like 3,800 hours per year that you actually need to heat. Now, for those of you who don't know, 8,760 hours in a year at 3,800 hours in a heating-dominated climate, you're well under half. You now have to heat like 3-ish months. So your heating system probably doesn't even turn on until like November. And it probably turns off in something like April. That's a pretty good number. And that's assuming that it's basically 40 degrees. The next thing you end up with is if you're in a super insulated house and you only need to heat once it's at 30 or below, you're looking at 1,700 hours a year. So at some point, if we look at those hours like miles on a car, if you only drove 1,700 miles a year, the efficiency of the actual car starts to matter less and less, right? Do you have a 4-cylinder? Do you have a V8? Well, if you only go 1,700 miles a year, you're really looking at 5 tanks of gas. So if you only need 5 tanks of gas a year, does it really matter if a tank of gas is $40 or $70? It becomes pretty inconsequential. But with these houses, you now need a very small boiler, and it doesn't need to come on for everything except for 2,000 hours a year. Like, that's where all the savings is. It's the fact that you're not running your heating system for beyond the majority of the year. You run it for less than a quarter of the year. That's where the savings comes from super insulated houses. But there's another thing going on there. When we talk about balance point, we usually are talking about the balance point for the heating, but there's also a balance point for cooling too. Now, Grandma's house, they didn't have an air conditioner, right? They grew up during the Depression. Who needs an air conditioner? That's fancy stuff for those people who live up the hill. So they probably had a balance point for 2 people in a 1,000 square foot ranch. If the comfortable indoor temperature was like 90 degrees, you probably didn't need cooling until it was like 85. That seems pretty reasonable. So we could even go farther than that, right? We could say 90 degrees inside, 80 degrees outside. Your child at home, everybody I remember, we built the houses for the 80s. We put some insulation in them. By the time you'd been in there for 5 to 10 years, they pretty much had air conditioners. Now, back then, when we bought air conditioners, you bought either windows or you bought the wall unit. Now, the wall unit was a window air conditioner that was too big for windows, so it slid in through the wall. Yeah, those were monsters. 1.5 tons, and then you plug it in. Crazy. Well, if it's 90 degrees inside, what temperature is it outside in a pretty well-insulated house? It ends up being something like 70 degrees. Now, if you think about being in that house, it probably isn't quite that crazy because you can open the windows and you can do other things. But to keep it under 80 in the house, it probably needs to be like 70 out. It needs to be less than 70 outside. So at 90 inside, yeah, it's 70-ish plus 75 outside. So when you then go to today's modern home, what temperature could you say, hey, air conditioner, never turn on again? Now, for 90 degrees inside, it's probably pretty close to 70, maybe upper 60s. But we're not comfortable at 90. We're comfortable at 80. So for 80, it might be 60 degrees outside. And you still need cooling. Just because all the things you're doing inside a house are still causing it to warm up. And it's just, can't get rid of it. If you're in a super insulated house, you probably need cooling under 50 degrees. Now, good news. Every hour you run that cooling system, when it's under 50 degrees outside, it's going to make a lot of cooling very cheaply. But have you been paying attention to the hours? Grandma's house, if it only needs cooling when it's above 80 degrees outside, she's talking about like 320 hours a year. Wow. Above 80, 380 hours a year, 400 hours a year. Most of them, you're not even home, right? You're at school, you're working, you're doing something. Yeah, grandma doesn't need an air conditioner. Your child at home, 2,000 hours? There's 2,000 hours above 70 degrees? That's a lot of hours to put up with being too warm. Today's modern house, 3,500 hours above 60 degrees outside. So there's a good chance that your air conditioning system's running 3,500 hours if it's well insulated, built to modern standards, and you have a central air system that just turns on and off when it thinks you need it. So now we're talking about a super insulated house. If it doesn't need cooling until something like 50 degrees outside, at 40 degrees outside, that's running 5,600 hours a year. Your house would need cooling to stay under this theoretical number, which I would say is probably 80 inside. For 90 outside, you're probably at 50 degrees. At 50 degrees, you're looking at about 4,500 hours of the year left. So it's over 1,000 hours more cooling, probably 2,000 more hours cooling for a super insulated house versus today's modern house. So maybe we're not just weaklings. We're not just soft, like our grandparents were saying. Maybe our houses can't cool off because we had the house that had the jacket that was fine when it was 60 degrees outside. And then we put the big winter coat over that, and then we were fine when it was 40 degrees outside, and then we put on the snowsuit over that. And now when we're in the warmth, we can't get rid of that heat. We get stuck overheating without even running our heating system. Now the problem becomes heating is really easy. We got really good at heating because we've needed it for so long. Cooling, residentially, we're not that good at. So I would rather have a house that's a little more balanced. And if you look at that modern home, the numbers, we're kind of solving for the right area, right? If you're in the modern home, you have about 3,500 hours of heating and about 3,500 hours of cooling. So you're under 4,000 on both. That makes sense. The problem becomes this is not a new problem. If you deal with a building that has about 1 square foot of exterior surface for every square foot of conditioned space, they've been cooling dominant buildings. So certain types of buildings like 2-story malls, massive city buildings, big office buildings have always needed cooling in the cores, and then the perimeters around the windows and exteriors, they've needed seasonal heating and cooling. We do that with free cooling using outdoor air or by using water that we cool off with outside. Hospitals, very much so. The difference is residential. We don't need that much outdoor air in your typical 1,000 square foot ranch, right? 200, you need 20, 30 CFM for 2 people in that 1,000 square foot ranch. And that's going to come in without even trying. So we don't run outdoor air to the building unless you're getting crazy tight. And we're only running 30, 50, 60 CFM. If you then ran enough air to cool that space with outdoor air, you'd be talking about almost 1,000 CFM for your 1,000 square foot ranch. If you run 1,000 CFM duct to your air conditioner and close that damper, you're going to get more than that 50, 60 CFM coming through the closed damper because its leakage is going to be on the order of 5%. And so just the leakage coming through that duct is going to increase your heating and your cooling by so much, it's not going to be cost effective. Oh, well, you could just open your windows. Well, you can open your windows when it's 80 inside and it's 70 outside. You can do it when it's 70-something inside and 60-something outside. When it gets to be 50 degrees outside and it's 75 inside, your house is going to create a pressure with the warm air. And if you're like in an upstairs bedroom and you're going to open that window to try to get some cold air in, it's not going to come in that room. It's going to come in lower in the house and the hot air is going to escape out the top. So if you have a super insulated house, it's actually hard to cool by opening a window. And if you run your air conditioner, depending on the type of air conditioner, it might have to heat the air conditioning compressor to make cooling when it's cold outside, because that condenser has issues operating really cold. And you'd rather it work when it's hot out than when it's cold out. So it's going to have to modify its performance so that you can actually make cooling when it's cold outside. We will figure this out. One of the problems with figuring this out right now is the limitation on the pounds of refrigerant that we put into systems. There's a couple neat things that people are doing now, using things like carbon dioxide as a refrigerant, using other things as refrigerants. And by using that additional refrigerant, we can circulate liquid through both sides to cool, which is a great way to do this. We can do other tricks with outdoor air. We can probably create some slightly more intelligent air systems that would be able to exhaust air instead of return it and bring in outdoor air. But those are still a little ways off. So, super insulated houses, Probably not right now. But there is potential, and there's a lot to come with ways that we can improve houses to be more tolerant of super insulating. The real problem with the super insulated houses is that they don't cool them. And you'll see this if you have a friend who has like an Instagram profile for something like, building envelope, passive house standard, super insulated house.com family. You'll watch, and all winter long the kids will be running around the house in shorts and a t-shirt because the house is 78, 80 degrees when it's November. So, that's a little thought. Couple things, interplay of empirical balance point versus calculated R value, some of the crazy issues that you'll have, and the way that things work in reality versus the design hour. It's a bit to mull over and chew over and to try to figure this out. We will get a handle on it once it becomes a problem that needs a solution. My recommendation would be try not to be on the bleeding edge. So, Passive House Standards has a lot of other good things in it. I would be just a little careful of how crazy I would go with my insulation if I was building that house today. So, for the Adding Energy podcast, I'm your host, Mick Lane. Thanks for giving a watch.